So the topic of this talk is, does the length of time of off-task behavior matter? And this is work by Daniel, Anthony, and Ryan Baker, and they're not here. So this talk is brought to you by me, who's only remotely related to this research, but hopefully good enough to explain. So yeah, and I'm not Skyping in, I'm just talking. So first I'll give a brief introduction. I'll explain how our data looks like and their data looks like and the model that they use to analyze this data, results and conclusion. Pretty generic outline. The focus of this talk is off-task behavior. Now, off-task behavior has been identified as a problem in learning for a very, very long time. We've all experienced this both as an audience and as teachers. I think a good example is just I hear the keys clicking around the room, and I can see the wireless bits running all around here. To see, yes, it's everywhere. And actually, there's also pretty conclusive evidence suggesting that off-task behavior is associated with poor learning. Now, this is the case also for, oh, now here's the mic. Can you hear me? Okay, good. Thanks. So off-task behavior is also a problem with online technologies. People can zone out whether there is a speaker or whether they work with the tutoring environment. And also within tutoring environment, it's shown to be correlated with poor learning. And I'll give an example of this later when we present the data. What is off-task behavior? We define off-task behavior as when student is completely disengages from the learning environment and task to engage in an unrelated behavior. So this is an example for behavior we observed. So my relation to this project is that I helped them at some point with data collection. For example, we saw students talking to other students. We saw students reading magazines in class. We're talking about middle schoolers in this case, surfing the web, playing online video games, sleeping, of course, very common, especially the more challenging schools where some kids don't have many other places to sleep in. And specifically, we collected this data in 2006, and most students were very engaged with transformers. So they did everything about transformers at that point, besides learning. Now, one hypothesis about off-task behavior is that there is a linear relationship between off-task behavior and learning. The general idea is that students simply lose the time that they're spending off-task, which is why there's a linear relationship. If I'm losing 5 minutes of being off-task out of 50 minutes, I lost 10% of time on task, 10% of learning. It's a very basic assumption or hypothesis. But there are reasons to suspect that the relationship between off-task and learning are not as simple and linear. For example, maybe short breaks improve cognition, right? We're overloaded, we just need 1 minute to breathe in, breathe out, and reapproach the problem. So maybe short breaks are actually good and productive. Maybe longer breaks are worse, even because we completely lose what was on our working memory and have to re-engage. Or maybe there's a common cause that I'm really much more disengaged if it's I take longer pauses. So now there is some interesting data that suggests that changing the length of observation periods affects the strength of relationship between off-task behavior and learning. So different studies found different correlation between being off-task and learning, depending on how they looked at it, which suggests that there may be a more complex relationship than the simple linear trend. So we decided to investigate the relationship between being off-task and learning gains by investigating differences between linear and non-linear models of this relationship between, again, learning gains and being off-task. And another thing is we looked at the percentage of time and number of brief and lengthy off-task episodes. So not just the overall time the students are off-task, but whether they're off-task for only brief moments, maybe multiple of them, or fewer longer episodes of being off-task. We studied this within the Cognitive Tutor, a very widely used family of intelligent tutoring systems, variety of domains, mainly math and sciences, few in language and programming. Now about 500,000 students use it every year. It's distributed by Carnegie Learning, which is a spin-off from Carnegie Mellon. And here is a messy slide, a sequence of messy slides to explain the cognitive tutor, what we see. Do you see? Yeah. So students, actually, the cognitive tutor breaks down the problem to students. It's very structured, very coached. Students type in, for example, here they need to type in the label for the graph or the x components of the graph. They have hints they can ask for. They have a skillometer. The cognitive tutor gives feedback and helps based on task analysis of the problem. So we know what skills are required to answer each of these steps. And these are traced here in the skills. Students may be good with labeling the axis, but not good with actually writing down the numbers, figuring out the equal intervals for the numbers, or not good with the y-axis, not understanding what y-axis means, etc. So cognitive tutors trace it, can give feedback on that. When the student makes an error, more common errors, the misconceptions are built into the system, so the system can give a very exact feedback that is tailored to the type of error that the student has made, which adapts feedback. Now, another interesting thing is that because the system traces the skill that students have and traces students' knowledge level, what we refer to as knowledge tracing, system can adapt the problem to the students. And that's pretty much, I think, what this slide says, yes. Okay. So this is basically the system. So it solve problems. In this case, it was data analysis and scatter plot plotting. And they get feedback when they're doing wrong. So how did the data look like? We had 186 students somewhere in the States that used cognitive tutor on scatter plots for about 80 minutes, 2 periods each. And we had pre and post test, 2 different forms counterbalanced. So randomly assigned in pre-test, and then each student received the opposite form for post-test. We did some field observations, so we just went to observe when students are off task. We had 2 or 3 different observers with a kappa of 0.74, which is not bad. Not brilliant, but not bad. And we had predetermined categories, and we trained each other. The observations were with peripheral vision. This was actually interesting. We want to observe students off task. When we're in class, students see that we are there. So we obviously change the off-task behavior pattern. So what we would do, we would on purpose stand behind a different student and look 2 aisles to the side. So hopefully students did not realize when they were observed. We all the time looked at students pretty far from where we were standing. Whether it had an effect or not, it's hard to tell. We assume not. We don't know, of course. We looked at each student for 20 seconds, categorized what the students did for these 20 seconds. 4 categories: being off task, which is again sleeping, etc. Gaming the system, which is trying to progress in the curriculum without answering. For example, I'll just guess all answers, right? I'm working on triangle. I know the angle should be between 1 and 180. So I have only 180 attempts until I get it right. Asking a teacher or another student for help. This is actually very interesting because when students talk to other students on topic, they do nothing with the system, right? They're not using the system, yet they're on task. It's a challenge to detect these automatically and working within the system. So actually going back here, what's interesting here that there's a kind of a 2x2. Students can be off task or talk with teachers. So these are things that don't happen with the system, but yet are productive or unproductive. And students can try to game the system or try to solve problems. Both happen on the tutor, and yet half of them, these are productive, half not. So the qualitative field observations give us an estimate of percentage of time the students are off task or gaming the system. And we use these to create an automated detector that identify all actions over time, which of them are related to off-task behavior. Basically, we build a latent response model. Roughly speaking, the x-axis here are actions. So you can think about it as time. And the first action, second action, third action. And each vector is a bunch of features that are relevant to this action. How long it took, what kind of interface element, was it a point or a pull-down menu, and what was the previous action, what's the estimated knowledge level, etc. Time of day, day of the week. All these are features that go to this table. And then we just run some essentially combination of these features to identify which of these actions is gaming. And we correlate the proportion of actions that are gaming with the proportion of action that we observed gaming. So we used our field observations as a gold standard for how much gaming was each student was involved in. And we looked for the model that will best match this across all students. So we take this matrix for each student, we get a number for each student, and then we have a vector of students. The vector of is percentage time gaming that each student was involved in. There was a whole bunch of fancy stats that I don't want to get into it due to time, but me or Ryan later will be glad to explain more. So essentially what we look for is a model that will generate the same percentage gaming as was observed. And the model achieved a pretty good correlation to off-task behavior, 0.55, under student-level cross-validation. Means we're taking a student out of the data. We don't train the model on this student. We train the model on all other students. Then we compare the model performance on this student. We see 0.55 correlation with what we actually observe. So this means that the model is pretty robust and good because it's being tested on students other than the students it was trained on. An interesting thing, it was a very low correlation to on-task conversation. So it can tell when students are off task and are really off task versus when students are off the computer but on task. Yeah, sometimes it detects a couple of actions after the action we really think the off-task happened. So actually in this analysis, we only looked at we define off-task as one of the last 5 actions and look at the longest period in the last 5 actions. Okay, now let me dive into the result, which is a more interesting component here. We use the field observation to evaluate the linear model versus the non-linear model. We saw, of course, a pretest is correlated to post-test, not surprisingly. What students come into their lecture with or to their class with predicts what they'll come out from the lecture with. Interestingly, the off-task behavior is also very strongly negatively correlated to post-test. So students who are more off-task learn less. Very intuitive, yet it's nice to see the strong correlation. It's also nice to see that it's fairly similar to the correlation with pretest. So pretest and amount of percentage of time to be off task, both pretty similarly correlated to performance, to learning gains, to performance at the end. Now the linear model predicting post-test is a good and significant model. The model is significantly better than chance, and the percentage of off-task behavior is significantly is a significant factor in determining learning. So the linear model that has post equals pre plus off-task time plus a constant is actually a significant model. The nonlinear model has off-task time squared, assuming that when a lot of off-task is worse than just very little off-task. And the squared, this model is also significant, but very similar. So we compared both models using a Bayesian information criterion, BIC. It's a way to compare models controlling for a number of parameters in the models. And we essentially got that the two models are equivalent. So we can't tell whether the linear or the exponential models are, or the power law model are equally good, or there is a difference in how good these models are. And the nonlinear model was slightly better, but not significantly better, so we should look more into it. Then we were curious about whether the length of each off-task episode. What we did here, we did median split of the off-task episodes as identified by the classifier. So off-task episodes that were long were classified as long. Off-task behaviors that are short were classified as short. And what is interesting here is that there was no relationship between the long and the short. And we actually lost the relationship that we had previously. So that's something that, well, certainly I cannot explain. I think also the people who did this research are still trying to explain. They're not really sure about why. But relevant to the research question of whether long or short episodes matter more, there is no evidence here that any type of off-task behavior matters more. It's the fact that they're off-task. It doesn't really matter whether these are long or short episodes of being off-task. And they tried also quartile split and again found no effects. So better, it's closer to being significant, but short off-task episodes are no significant factor in learning gains, and long off-task episodes are not significant factor in determining learning gains. Okay, let me try to conclude what we briefly went over here. Percentage of time off task. Well, first we thought that both linear and non-linear models predicted learning successfully. So we can't tell which one is better. There's no significant difference between the two models. There is a trend for non-linear, but we should further look into it. What was established again here is that the fact that students are off task is a significant factor in not learning. Length of off-task episodes, we didn't find a difference, or they didn't find a difference between brief and lengthy episodes of being off-task. And the data set was fairly focused for this analysis. I didn't want to go too much into detail, but they actually took a subset of the entire data they had, and maybe there was something weird about this data, of course, yet to be known. And that's roughly it for now. No ground to reject the time on task hypothesis, a linear hypothesis. No sufficient evidence to suggest complex relationship, but some issues that worth further looking into. And I think what's interesting for this conference is the idea that we can look this microgeneric per second data to try and understand learning behaviors, not only looking over time, but also looking within time. Thank you. I could try and get a couple of quick questions, but I'm not sure I'll be able to help much.
Okay.
I'm just fascinated by the task itself, which seems like one that where time on task would be very important. But I don't know. Do you have any thoughts on, or do they? Is there any evidence from what you know of this, whether different tasks? I mean, for example, some reflective or more creative learning processes, I would hypothesize would benefit from daydreaming.
So I can. I guess and hypothesize. So I personally work on these more creative tasks. And I agree. I think that actually these pauses are extremely important. I don't know whether I would say daydreaming is important or still being more focused. What we did find, which was interesting, looking again at a very constrained task such as this one, we look at the difference between different interface elements. And we saw that the type of question is very significant determiner of whether students are off task or not. So when students have pulled down menus, they'll often be on task, but they'll often try to game the system. They'll just use all options because coming up with the right solution is easier than thinking, so they won't think. The more challenging the task is, for example, an open-ended answer, the more students will be likely to be off task.
I'm just wondering if the off-task here relates to how much progress they make through the system. Since they're doing it in school during a class period, if you're off-task, you're not getting through as much of the content. You're not working your way through the tutoring in the steps, so you just end up being short on what you're supposed to get through. If they had a longer time, like if you had to just sit there until you completed a module where you were sitting there longer, if you're longer off task, if you'd find the same relationship between performance and off task.
That's a great question because we haven't looked at it and we could. So the cognitive tutor curricula is mastery based, which means the students do move on only when they complete the activity. And they know it. They know that I showed you the golden bars. They know that they should get the golden bars all the way through. So you would think that they'll be less off task because they know that they're wasting their own time. We didn't compare off-task behavior in mastery-based system to a time-based or a fixed curricula system. Right? The curriculum adapts you to the students. As long as they don't master the skills, they'll get more and more practice. We didn't compare it between adaptive and non-adaptive system, and I am not familiar with studies of off-task in non-adaptive systems.
Okay, anyone else? Yeah. One more. We have time for one more.
It's a kind of a question, kind of a comment, but I think the point you make about looking at time not just in the big picture and over scales, but within learning experiences is quite important. And I think one thing that might make this more interesting is to look at when, not just how long, but when they're taking the off-task breaks, because what we've found is that students often exhibit very interesting patterns of what they're doing when. And so, for example, big breaks at the beginning may mean thinking, at the end it may mean that they're fading off, and we've seen a big difference when we start to look at that part of the equation as to getting more predictive power in what the breaks are meaning.
Yeah. So Yes, it's great that you took what you talked about yesterday and returned, right, because as you know, as we talked about yesterday, I completely agree with that. The time is extremely important, especially when we, again, go back to more reflective activities, more creative activities. We'd like students to be more creative maybe at first, when they have time, even as groups, right, to more brainstorm and think. When it's time to execute, students should be more focused and concentrated. What we did find was very interesting in this, going back to this constrained environment and the parallel topic I'm slightly more familiar with, we studied gaming the system. And we found that there's a whole bunch of students who game the system, but not all of them. So again, trying to guess until they get the answer or exploit help facilities. Not all students who game the system were hurt by this. So some students tricked the system and yet learned. So after we got these results, we went back to find out what's unique about them. And we found that some students game the system on skills that they know. So on the easy problems that are easy to them, they game the system, they were fine. So these are students that are bored, don't feel like calculating again, they know it, they were fine. Students who game the system on the difficult questions suffered from it. So again, we have an interaction. It's not just gaming is bad. There's an interaction between gaming and the challenge level of the skill that determines whether it's productive or not. And I'm sure that Ryan will be happy to tell you more about it. Okay. Thank you very much.